Hi everyone, my name is Raquel Urtasun and I'm the Chief Scientist at UberATE as well as a professor at the University of Toronto. Today I will be talking about simulation as the key to scale self-driving autonomy development, model training, verification, and testing. A critical component to making self-driving vehicles a reality is verifying they are safe. For example, how can we properly evaluate that a self-driving vehicle will perceive and stop for a duck, an actor we might rarely see? Or how do we make sure that the SDV will stop in time if an occluded actor suddenly enters our lane? The self-driving industry uses a combination of three different approaches for evaluating and testing SDVs. First, there is structured testing, which tests the SDVs under a set of reproducible scenarios. This is typically done at a test track facility. This test setting is considered high fidelity since we can evaluate the full autonomy system and hardware of the car in the real world on a particular scenario. We also consider this testing to be reactive. As the SDV perceives the scene and performs a maneuver, the other agents in the real world can respond to its behavior, and the sensor observations are accordingly updated. While effective, structured testing currently has some limitations. It's difficult to test extreme or dangerous situations such as high-speed avoidance maneuvers. Additionally, large-scale testing is impractical. We can also evaluate the SDV on pre-recorded real-world data. This potentially provides a more realistic setting for urban driving scenarios compared to structured testing. However, this simulation is not reactive. The sensory data and other actors' behaviors are not updated according to the SDV's actions. It is also still difficult and potentially unethical to collect and test safety-critical cases at scale. The third method is to use simulation. While simulation systems have a domain gap with the real world, simulation has some significant advantages. The agents and the environment in simulation can be reactive. Simulation allows testing any safety-critical scenario easily. And more excitingly, simulation has the potential to be scalable. Not only can we perform millions of different evaluation tests, we can also use simulation for training different autonomy algorithms. We now review the self-driving vehicle autonomy system and how we can inject simulation for evaluation. Every fraction of a second, the vehicle senses the environment. The perception system is then responsible for estimating where the objects are in the scene. The prediction system then predicts the output of perception, then takes the output of perception and estimates the potential trajectories that the actors might take in the next few seconds. Then the motion planning module focuses on a region around the self-driving car and estimates the safest maneuver towards the goal that the vehicle should do in the next few seconds. Traditional simulators only simulate bounding boxes trajectories, enabling only motion planning evaluation. This is a typical approach in industry due to ease of running and relatively low overhead. It makes the assumption that the self-driving stack is modular and just uses active dynamics for traffic simulation. End-to-end closed-loop testing of the full autonomy system requires going farther than just simulating bounding boxes and trajectories. We need to have a complete simulation system that models the real world accurately. To build such a complete simulation system, we need to animate the dynamic state of the environment, where we have actors, including vehicles, pedestrians, and cyclists, construct geometry of both the static environment and the dynamic actors, and finally, simulate the sensor observations the SDV receives. We begin our discussion with simulating the actor dynamics, and we refer to this component as LidarSim. The goal of LidarSim is to generate active behaviors that are high fidelity, realistic, in that it models human behaviors well, and diverse, in that it covers all plausible behaviors. These attributes are critical to enable the main application of this simulation system, training and testing the SDVs on unseen, rare, harmful events that can happen. Understanding and replicating human behavior is a key theme in both autonomy development and simulation. But there are key differences between the requirements in actor simulation and those in prediction and motion planning. In motion planning, the goal is to generate the safest and optimal trajectory plan. Even though we might learn by imitating human driving, we are interested in learning only the best driving behavior. Whereas in active simulation, we are interested in recovering the full distribution of human behaviors, which includes potentially reckless maneuvers. In comparison to prediction, where we have partial and noisy observations, we might assume perfect information about the environment and other actors. This enables us to centrally coordinate actors to create scenarios if necessary. Most importantly, active simulation is a closed-loop task, where previous plans influence future states. In other words, the underlying task is a sequential decision process, and we cannot make IID assumptions. There is a spectrum of fidelity with which we can animate the dynamic actors in the sim. At the simplest and inflexible end of the spectrum, we can manually specify fixed trajectories for each actor to follow in the sim. This is in fact how most test scenarios for SDVs are specified. At a more advanced level, actors can execute simple lane following behavior, given a fixed route to follow. But these approaches are all gross simplifications of the real world. To arrive at a model with high flexibility and fidelity, it is necessary to capture complex non-compliant behaviors, which include lane changes, cutting corners, U-turns, etc. Different styles, such as aggressive, cautious, and interaction, such as yielding and coordinating. Different use cases of the simulation system require different degree of fidelity. When evaluating SDV's reactive capability, it's often sufficient to specify fixed trajectories for actors of interest, since they do not need to react to the SDV. But when evaluating the SDV's proactive capabilities, such as merging onto a busy lane, we need to accurately model how an actor yields to the SDV. Lastly, to evaluate SDVs in general complex and sim traffic scenarios without handcrafting them, we need the biggest fidelity actors to automatically generate interesting, challenging traffic flow. Most teams in the self-driving industry are still relying on traditional engineering approaches, which are limited in fidelity. Learning-based approaches have shown promise in developing high-fidelity actor models, as they leverage and scale with the abundance of Lego data. Direct policy learning and event reinforcement learning are popular learning-based approaches. While there are a suite of different sensors that can be helpful on the self-driving car, such as LiDAR, camera, radar, IMU, infrared, and so on, we focus our discussion today into LiDAR and camera, as they are the sensors most prevalent in self-driving cars. Sensor simulation of LiDAR and camera data is a challenging topic. Both sensors require building a virtual representation that accurately models the geometry of the real world, and then performing realistic rendering of the scene. For realistic geometry, the field typically splits the problem into two components: background scenes, such as roads and buildings, and dynamic agents, such as vehicles or pedestrians. After building geometry, we generate sensor observations. I will now discuss LiDAR simulation for self-driving. Here we show a LiDAR sensor on one of our vehicles. There are two primary ways in the field to simulate LiDAR: graphics-based physical renderers and data-driven approaches. I will discuss both of them now. The standard graphics, such as simulation approaches based on game engines, like car LidarSim, simulate LiDAR by designing 3D assets by hand, building a virtual city, and then physics rendering the LiDAR. The advantage and disadvantage of graphics-based engine simulation is explicit world and physics modeling from the ground up. This allows for total control of the world and precise definition of all the assets. But unfortunately, it is expensive to create these assets. It is not scalable to have virtual worlds for the numerous cities we want to test, and the simulated LiDAR is also unrealistic typically. One reason why the previous LiDAR simulators are unrealistic is that game engine simulators use low-poly assets to speed up sensor sim, and don't properly model LiDAR physics, such as material reflectance properties or the specific calibrations of different LiDAR sensors. Blender attempts to model this with enhanced graphics modeling of physics and calibration. Unfortunately, enhanced graphics suffers more so from the issue mentioned earlier, with the additional disadvantage that simulation is slow. They report a single LiDAR shape takes 8 to 9 seconds per frame to generate, preventing scalable autonomy testing. Data-driven approaches instead show how we can use sensor data collected from the real world to build 3D assets, and then apply rendering to simulate the LiDAR. This recent work shows off-road terrain LiDAR simulation by generating assets of vegetation and road. It will be very desirable to have a similar approach for LiDAR simulation in the urban driving environment that we are interested in. That is what AADS LiDAR simulation does from the Baidu Apollo Research Group. They use a high-end LiDAR scanner to collect highly accurate background scenes, which they combine with a collection of CAD models and probabilistic scene generation to generate LiDAR sweeps. This approach is promising, but is still constrained in scaling due to the set of CAD models that it requires in order to create the simulations and the use of an expensive scanner over $1 million to create the virtual world. It also does not fully model all the physical effects of the LiDAR, such as the rolling shutter and motion blur of the actors. Our work, which will appear at CVPR this year, is called LidarSim, and builds on the past work by incorporating both graphics and data-driven approaches, along with machine learning. LidarSim builds assets at scale using a fleet of self-driving cars with standard sensors, and then uses physics with machine learning to generate realistic LiDAR simulations at scale. I will not discuss in more details the different components of LidarSim. LidarSim leverages millions of real-world miles collected by our fleet of self-driving cars to help build virtual worlds for autonomous vehicle testing. On the right, you can see the reconstructed background scenes of an intersection and a collection of the different dynamic objects created from LiDAR data. Here we show how LidarSim generates realistic backgrounds. We record real LiDAR data by driving in an area and remove moving objects using automatic 3D semantic segmentation. We aggregate and align the LiDAR, combine across multiple trajectories, and create a mesh for representation of the background. A similar process is done to generate dynamic objects. We utilize a symmetric prior to get a complete shape of the object. Leveraging real data allows us to inject the diversity of objects seen in the real world into LidarSim. From left to right, we can see cars with open hood or trunk, bicycles on top of the car, flatbed trucks with construction cones, and trailers with extended cars. Making sure we can detect these rare objects as vehicles is important, and by leveraging real data, we can simulate more situations that are in the long tail. You often don't see the diversity of these 3D assets on CAD model datasets. Once we generate our assets, we can place them in a scene configuration, just like in a video game. We now have scalable and diverse scenes. We then perform realistic sensor simulation with a combination of physics and machine learning. LiDAR generates point clouds by shooting light into the scene and measuring the travel time to determine an object's distance. To mimic this process, we recast our scene and generate a simulated point cloud. However, raycasting generates more returns than real LiDAR, since the return light does not always meet the detection threshold. We call this phenomenon ray drop. Ray drop is complicated to simulate by physics alone, because we don't know the physical parameters of the real world. Fortunately, using a ray drop network will leverage real-world data and ML to bridge the scene-to-real gap. We convert this LiDAR sweep into a spherical image representation, encoding features related to ray drop, such as range values, incident angle, semantics, and path intensity values. We then feed these features into the network and predict how likely a ray will be dropped. The labels come from real LiDAR ray drop patterns. We sample the ray drop probability to generate the final point cloud. We now show results. Green boxes here indicate vehicle detections from a model trained on real data only. This side-by-side comparison shows that LidarSim generates realistic point clouds with a small domain gap for downstream perception tasks and autonomy testing. We now compare LidarSim against Carla, a state-of-the-art sensor simulator. A model trained with Carla data and tested on real data has a large sim-to-real domain gap, but a model trained with LidarSim has just a 1% domain gap, significantly outperforming Carla. The small domain gap means LidarSim is effective for data augmentation. By combining LidarSim data with real data, we gain a significant performance boost for vehicle detection with both small and large amounts of real data. LidarSim also allows us to evaluate a perception and motion planning system maneuvering safety-critical scenarios in a closed-loop setting. Here we see a simulated scenario where a vehicle turns into the SDV's lane, occluded by a bus. The system, trained only on real LiDAR data, is able to process LidarSim data and safely brake to avoid collision. With no additional training or domain adaptation, we can directly use LidarSim to test an autonomous system end-to-end on millions of different scenario variations, achieving results that match closely with the real world and allowing us to gain new insights. Along with LiDAR, the camera sensor is another critical component for most self-driving autonomous systems. So we are going to now turn our attention to camera simulation. Modern autonomous driving car platforms are equipped with multiple high-resolution cameras, covering different viewpoints, for example, front view, side view, and rear view. This requires us to simulate camera images which are consistent across viewpoints and time. I will first review graphics-based camera simulation and recent progress in using neural networks for camera sensor simulation. I will then present two recent efforts towards photorealistic camera simulation at this scale from the lab, which are shown today for the first time. Graphics-based camera simulation relies on classic rendering techniques. On one hand, real-time rendering is cheap and efficient, but does not produce photorealistic sensor data. On the other hand, high-fidelity rendering is very expensive and hence not scalable, as it usually takes a few hours to render a single image. Recent neural rendering methods formulate the camera sensor simulation as the problem of conditioned image generation through semantic layout to image translation, domain adaptation, and image manipulation. However, these single view-based methods cannot be directly applied to create the virtual environment for self-driving cars, as the simulated camera images are usually geometrically inconsistent. Other methods insert 3D vehicles into the scene by encoding and manipulating semantic image representations, or manually specifying vehicles in new locations and rendering them. However, this requires very expensive manual editing and hence is not scalable. In addition, these approaches do not have a 3D scene representation, making them difficult to extend to video or for handling interactions with other actors in the scene. In contrast, I will present now two novel efforts towards photorealistic camera simulation by leveraging existing camera sensor data and the 3D geometry of the scene. First, we study the problem of dynamic object removal from the 3D scene. The output of such a process can be used as a blank state for adding virtual dynamic objects. Second, we study an inverse problem, namely, inserting dynamic objects into the scene in a geometrically consistent and physically plausible manner. As we automate camera simulation in both efforts, we can create a great amount of scenarios that potentially capture the diversity in the long-tail distribution of driving data. So let's go over the first work. Given a sequential multi-sensor data in the form of multi-view camera images and sparse LiDAR point clouds as input, we design a smart 3D editing program that is capable of removing all dynamic objects, for example, vehicles and pedestrians, in the scene and recovering background structures such as buildings, road, vegetation, and sidewalks. Towards this goal, we first reconstruct the 3D geometry of the scene and then propose a data-driven approach based on the reconstructed geometry. Core to our system is a novel geometric-aware inpainting network that learns to remove dynamic objects from the 3D scene. The proposed network works in a coarse-to-fine manner. The coarse network learns to make the initial predictions of the image, depth, and semantic layout on the region to be inpainted, while the refinement network learns to generate detailed textures from those predictions. We refer to the initial predictions from the coarse network as the intermediate multimodal representations. To enhance the perceptual consistency over time, we introduce an additional temporal feedback. Given 2 frames, the predicted output at frame 1 is reprojected to frame 2 and passed back into the generator for inpainting the second frame. Our temporal feedback is built into the model itself and is trained end-to-end with the rest of the network. Finally, we introduce a novel geometry-aware temporal attention model that copies and borrows features from the visible regions in other frames to the target regions to be inpainted. Since our approach is efficient, we can exploit a large temporal window. This is achieved by computing the feature similarity between the pixels to be inpainted and the spatiotemporal tube on the reprojected images centered around the corresponding pixels. This is efficient as it requires only a minimal number of candidate patches during training and can also dynamically scale to make use of more or fewer views depending on the computational resources. In this video, we provide a side-by-side visualization of the inputs. Of the input video, the output from the proposed method, as well as results from 2 state-of-the-art video inpainting algorithms. Our approach generates more photorealistic and geometrically consistent results as we leverage the 3D geometry explicitly through our network design. In contrast to existing video inpainting works, we take advantage of the geometric correspondences with longer time horizons, which really helps our approach. We now show the opposite problem, which is inserting dynamic objects into an existing video sequence and generating a photorealistic video of the augmented scene. So let's go over it. Let's start with a question. Which of the objects in the depicted images are fake? Let me give you a few seconds. Did you guess correct? What you just saw is GymSim, a novel approach that leverages active sim as well as 3D geometry of the scene to simulate camera sensor data from multiple viewpoints which are geometrically consistent. GymSim takes advantage of recorded camera data, LiDAR sweeps, and 3D bounding box annotations to aggregate real-world sensor data for dynamic objects encountered in the wild. Such data is readily available in modern self-driving datasets. With our approach, we can generate a large-scale and diverse 3D object bank with precise geometry, high-definition appearance, and accurate 3D poses. To build our assets, we develop a 3D reconstruction network that takes camera and LiDAR sensor input from multiple viewpoints for a given dynamic object and outputs a high-precision 3D shape. Specifically, we process and combine crop LiDAR point clouds and images into a single feature embedding, which we then use to predict the formations to a min template shape prior. We then perform energy optimization on the predicted shape to make sure it agrees with the input LiDAR and images. Note that we don't require any ground truth 3D shape data. Here are some examples of 3D assets which we reconstruct with our approach, as well as the corresponding images. Note that we can model vehicles of different sizes and shapes. We then place 3D assets onto the high-definition map so that they reflect the traffic and 3D layout in a realistic manner. Note that our object placement is not only 3D aware, but is physically plausible and temporally consistent. we leverage an intelligent driving model for simulating the vehicle's trajectories over time and making sure it has realistic acceleration and braking such that the full scenario is coherent and realistic. We use a novel view rendering with 3D occlusion reasoning with respect to all elements in the scene to create the appearance of the novel object in the new camera image. We finally generate photorealistic camera simulation using a post-completion image synthesis network, as depicted here in the image. Unlike existing work on neural image synthesis and manipulation, which either requires human interaction, is not realistic, or only models it to the context, our approach is fully automatic, photorealistic, and 3D layout aware. We compare the proposed GymSim with the state-of-the-art 2D neural rendering methods, as well as a retrieval-based copy-paste baseline. Compared to 2D-aware image generation models such as Pix-to-Pix HD or guided editing, GymSim produces much more realistic augmented images with little to no distortions or aberrations. And compared to a single copy-paste baseline, we can see the value of GymSim's 3D-aware placement and occlusion reasoning for a reasonable image scene, along with inpainting to remove boundary effects that otherwise would be visible. We also measure the perceptual realism of the simulated images using A5D. Our method is capable of producing significantly better quality images than the state-of-the-art. To further verify the realism of GymSim, we conducted a human A/B test. We show a pair of images generated from different approaches on the same background real image, one from GymSim and another one from a competing algorithm to the users. We then ask the human judges to click the one they believe is more realistic. From over 20 users and close to 5,000 images, we can see that GymSim images are preferred more than 94% of the time, and with respect to some of the baselines, even 99% of the time. This confirms that there is a significant gap between other baselines and GymSim that is immediately noticeable to humans. In addition, we conduct downstream perception tasks, including image segmentation, 2D object detection, and monocular 3D object detection on the simulated images and compare the performance with real images. We now show how perception algorithms trained on real data perform on images generated from the different simulation baselines. We first show the results on real images. The numbers in the parentheses indicate the performance gain or loss using different simulations. Here are the results of the different image generation baselines on the different tasks. We want to emphasize here that a higher IP or mean IOU perception metrics on simulated data is not necessarily better. Instead, we want the perception metrics to closely match the perception on real data. This difference is reported in the parentheses. The closer the metric on simulated images matches with real, the more likely the perception algorithm considers the simulated image as being from the same distribution as the real data. As we see in the table, there is a clear difference between using real images and synthetic images generated by 2D-based neural inpainting methods. In contrast, the proposed GymSim not only produced visually plausible images, but also the perception algorithms trained on real data alone will generate consistent results reflecting the correct semantics in both GymSim and real data. Let's go over qualitative results. Here is an example of a scene with a simulated object. Can you tell which one is the simulated? Notice that we can simulate objects at different and diverse viewpoints, front or back, close or far away. We can accurately handle occlusions with static background objects, other vehicles, and even pedestrians. Even more exactly, we can extend our geometry-aware image simulation by composition approach to video simulation. Notice that our simulated images are temporally coherent and that the added objects obey traffic and have reasonable motion. Multiple objects can be added to the scene and interact with each other, for example, performing lane changes. Being 3D aware also means we can also do multi-camera simulation that is physically possible. In this case, this will be 2 cameras mounted in different locations in the self-driving car, how they will perceive the scene. We hope GymSim is the next step in providing realistic camera simulation for autonomy testing. Thank you. In summary, full autonomy testing and training means we need to have multiple components. To build such a complete simulation system, we need to animate the dynamic state of the environment, where we have actors including vehicle, pedestrians, and cyclists, construct geometry of both the static environment and the dynamic actors, and finally simulate the sensor observations the SDV receives. We're excited about simulation. There is a lot of exciting areas for the community to explore. Simulating all kinds of sensors, building the world, and automating the training and testing of what matters most. Thanks for listening.